Hello, everyone. Welcome back. Today, we're going to be talking about unimolecular nucleophilic substitution, which is also known as Sn1. And so, this is the second lecture in a set of four that is relating to a set of reactions that are called the Big Four. And these reactions are essentially the four reactions that are kind of leading into everything that we need to know about organic chemistry. And so, SN1 is just going to be our second one in the series. But the first thing is last lecture, I did promise that there was one last thing to talk about for SN2, and that is solvent effects. So before we get into anything with SN1, we're going to take a quick look at solvent effects in SN2, because these will also come up for SN1, but essentially we need to talk about both today, so we will. So in SN2, right, remember the SN2 previously we talked about it as being this reaction where we have some type of leaving group. Let's say it was a bromide and we throw in something like sodium cyanide, right? What's going to happen is essentially in the mechanism of this reaction, we would have the leaving group getting kicked out by a backside attack by the nucleophile, which in this case is that Cn minus that comes around. It does a 180-degree attack, displacing the leaving group bromine, and you have then substituted your nucleophile onto that position. And so essentially, this reaction works really well, but the thing is, it also depends a lot on your solvent. And there's two different types of solvents that we can actually look at here. The first type is what we're going to call polar protic, and then the second type is polar aprotic. Right, and so the differences between these two names, you'll notice, is just the A in aprotic, or missing it in protic. And essentially, that's just telling you whether or not the thing is sort of an acid. All right, because essentially, polar protic solvents, they can act as hydrogen bond donors. All right, and so what that should tell you is these things are usually molecules that have a heteroatom such as oxygen, nitrogen, fluorine that's connected to a hydrogen, right? So these are also usually weak acids, right? And so, like I said before, it's things that have that OH, NH, FH, etc. So some examples of these would include things like water, right? A very good hydrogen bond donor. And it's also, protic because it has those protons on them. Things like ethanol, right? It has that OH, right? All of these have these specific oxygen hydrogen paired together. Something like diethylamine, right? This one has that NH, or even some relatively good acids like acetic acid have that OH that can act as a hydrogen bond donor. On the other hand, polar aprotic solvents are the opposite. They do not have that proton to act as a hydrogen bond donor. So these cannot act as H bond donors, right? And so these, we would say, usually just have heteroatoms with bonds to carbon, right? So we're thinking usually oxygen, nitrogen bonded to carbon. And the reason for that is because all of these are no, they're polar, right? They're not just completely non-polar things. They have to have some type of dipole. So some examples of these, we have a little bit larger of an arsenal for a lot of these. And these are going to be some solvents that have specific names, right? So we're going to go through and we're going to kind of look at these solvents, and I'm going to give you their abbreviations because you'll see their abbreviations as well. Right, for the others, we've talked about many of those types before, but this guy right here is tetrahydrofuran, which is also known as THF when it's abbreviated. So if you ever see THF, you think, oh, it's going to be this molecule here. All right, and these are just going to be quick solvents to memorize. Another one of these that has a short abbreviation is this one here, dimethylformamide, or DMF. Right, and so you'll see that DMF also has this idea of these oxygens and nitrogens that are bound to carbons that are essentially creating a dipole. right? Notice that there is a hydrogen that's shown in the DMF, but it's not bound to an oxygen or a nitrogen, so it can't act as a hydrogen bond donor, right? Another one of these types of molecules is DMSO, or dimethyl sulfoxide, right? And so this one contains an interesting sulfur oxygen bond, but it's still just the same idea. It's polar aprotic. Same thing with a solvent like acetone, right? You all have likely used this quite a bit in lab, right? Acetone's good for cleaning glassware, but it's also a relatively good solvent in terms of acting as a polar aprotic solvent, right? And then the last one that we'll talk about is one called DCM, dichloromethane. It has two chlorines there that are giving dipoles. Right, so there's a lot of polar aprotic solvents. These are the most common ones that you're going to see. But essentially, what these two types of solvents are doing is they're changing how nucleophilic something is. Right, essentially, nucleophilicity depends on the solvent. And to show this idea, we're going to once again use that sodium cyanide, but we're going to look at it in terms of what solvent we put it in. Right, so let's say we took the sodium cyanide and we put it into a polar aprotic solvent. So let's say we chose acetone. All right. So thinking about sodium cyanide, normally we would say that this thing is split into a sodium cation and a cyanide anion. And then acetone is just chilling out as acetone. But as a reminder, this guy has a partial negative here and a partial positive on the carbon. But the partial positive on the carbon is not very strong, right? Essentially, we don't think about that as much when we're looking at this. Instead, it's mainly this partial negative that matters for us whenever it's acting as a solvent. And the reason for this is, let's say we split up that sodium and that cyanide in this solvent. What would it actually look like? Well, what we would have is the sodium would actually be surrounded by molecules of acetone. And the reason for this is because all of these partial negative charges are interacting with the sodium. And what it's doing is it's allowing the cyanide over here, right? It's essentially separating it from its anion, or I guess from its cation, thus making it stronger. Because remember, if it's paired with the sodium, essentially it's making an ionic bond that is very neutral. But in this case, it has that full negative charge at its disposal. All right. So the more you can isolate these things, the better off they're going to be. And how this looks in water is completely different. Because you can imagine sodium cyanide in water is going to take a very different approach. Since we have, in this case, the cyanide with a negative charge, right, it can actually act as a hydrogen bond acceptor. And so what this means is if the water is hanging out around here, all of these hydrogens, keep in mind, have partial positive charges. Not only do they have partial positive charges, but they are attached to an oxygen, which makes them able to be donated through hydrogen bonding. And so if we show this as a hydrogen bonding network, essentially you'll notice that all of these hydrogen bonds are stabilizing the negative charge, which essentially makes it less reactive, right? Because remember, when we're thinking about stabilization, we're essentially dropping it in terms of energy. So if we're doing an SN2 reaction here, and we have in one case, let's say that the blue line is in acetone, and then the red is in water. What we would see is in acetone, the Cn minus is very unstable because it's separated from anything that's giving it stability. So essentially here, right, it's going to go through the reaction and it's going to have a relatively low activation energy to get to the products. But in water, the cyanide is very stabilized. And so because of that, it's still going to have the exact same activation energy and the exact same product energy, or sorry, it's going to have the exact same peak energy, but its activation energy is now much, much higher than it was in acetone, right? And so what this means for us for SN2, essentially polar aprotic solvents are going to be better than polar protic solvents, right? Just because essentially we're stating that in polar aprotic solvents, we are making a more reactive nucleophile than we are in polar protic, which is a less reactive nucleophile. Now, this would be great and all if it wasn't for some exceptions, right? And the big exception here is size. Just like we talked about last time with size, it acts as an exception in terms of nucleophilicity. But that's not always true. I was just using that as a good example because it depends on the solvent, right? Because you can think about it. In the case of in water, let's think about F minus versus I minus, right? So fluoride is relatively small. And so you can imagine if it's chilling in water, right? Fluorine is very happy to be a hydrogen bond acceptor, and so it is being well stabilized by all of these waters. Versus something like iodide, right? I minus, it's huge. Okay? And so if we think about what the water is going to be doing here, right? Notice that for the same amount of water, it can't cover the entire surface area. Okay? And so essentially what this is doing is now these are trying to make these hydrogen bonds, but essentially there are still very large areas of the surface that are available for reactivity. And so what this is actually doing is it's actually polarizing the molecule to where it is allowing these open spaces to react even easier than if they weren't in water, right? Because it's concentrating the charge onto those spaces, which a more concentrated charge is usually a better nucleophile, right? So what this means is larger ions react faster in water. Okay? And so in water, iodide is a better nucleophile than fluoride, but in acetone, it's actually the opposite, where fluoride is a better nucleophile than iodide. Right? So what this tells us is that nucleophilicity is also solvent dependent. For that reason, whenever you see reactions with iodide, right, let's say we were to take a look at a reaction that uses something like sodium iodide, nobody will actually run it in acetone. What they'll instead run it in is something like ethanol, right? Because ethanol, as a polar protic solvent, right, is going to be better for the large iodide. And in doing so, it'll do the SN2 quicker. Now, this is in comparison to something like we were looking at beforehand with sodium cyanide. No one would ever use ethanol. Instead, they'll use something like acetone, right? Because this being polar aprotic, it is better for the small cyanide ion. Okay? So on the exams, just keep in mind that you will likely see polar protic solvents being used with something like iodide, but you will see polar aprotic solvents being used with something like sodium cyanide. All right? Now, with all of that being said, now we can move on to the main topic of discussion for this lecture, which is unimolecular nucleophilic substitution, also known as Sn1. So, Sn1, of course, is telling us that we are doing a substitution. All right. And so, what this one actually looks like is it's very similar to Sn2. For this one, though, we're going to be using actual molecules instead of just saying leaving group and nucleophile, because it's going to be very important for us to see all of these as we go through. Right, when we're thinking about an SN1, usually it looks something like this, right? What we're seeing here is that SN1 needs a weak nucleophile and a good leaving group, right? This is contrasted with what we saw for SN2, which needed a strong nucleophile. And so we need to think about why this is the case, right? Why would this pathway occur instead of SN2? And the first way that we need to think about it is once again in terms of energy, right? Because essentially what we're looking at is if we think of our reaction progress, right? This methanol up here is a weak nucleophile. And we showed last time that if you used the deprotonated version, it would do an SN2 process. And so the reason for this is entirely due to if we think about our energy diagrams, right? Looking at something like methoxide with our bromide, right? It can come around and do this SN2 process just fine. But if we wanted methanol to go through and try and do this SN2 process, we have a little bit of a problem because both of these are essentially creating the exact same product in terms of energy, right? But notice that in the case of the methoxide, it has a very relatively decent activation energy versus the methanol, it's got to go way up here just to form the same level of products, right? So our difference here is we have a huge difference in activation energy. Even though in the end we end up with the same energy of products, the activation energy for the SN2 process using methoxide is much lower. So essentially what we're saying is due to the methanol stability, the activation energy is much higher. What this means for us is it can't go through the SN2 pathway. The activation energy is actually too high. All right, if you were to calculate it out, you'd find that it is actually ridiculously high, right? So we can't go through an SN2 pathway. So essentially, what we got to ask ourselves is what else could we actually do? And this is where the mechanism of the SN1 gives us some ideas, right? If we can't go ahead and do a nucleophilic displacement, there's only one thing that we actually can do, and that is a two-step mechanism where first the leaving group leaves on its own, right? What this does is it's going to create a carbon that is missing an octet, right? It is an unstable carbocation. But the benefit is, now that it is a carbocation, it's not as sterically hindered for our methanol to come in, take the reins, and add to that position. Because remember, with SN2, the main reason that our activation energy is high is because of the steric bulk that surrounds the leaving group. All right. So upon addition, in this case, we then end up with this entire group, the methanol being added on, which means there is an additional proton, which means our oxygen has a positive charge. That means that something else has to come in and take that, and in this case, it's going to be methanol. And the reason for this is because methanol is both our nucleophile and the solvent, right? Notice how when we were looking at the original reaction conditions, methanol is the only thing listed there, right? Which means that it must be both the solvent and the nucleophile for us. And that's true of a lot of SN1 reactions, and we'll talk about why in just a minute. But this reaction differs a lot from SN2 because it's going to end up taking a lower activation energy pathway, but it ends up with an intermediate that is unstable, right? If we use BDEs to approximate our delta H for each step, right? The delta H for step one, we break the CBr bond, which means that our delta H is plus 68 kilocalories per mole here, right? Our delta H for step two, we form the oxygen carbon bond there, which is actually a negative 91 kilocalorie per mole step. And then our delta H for step three, this acid-base reaction, we're forming an OH bond, we're breaking an OH bond. It's actually a 0 kcal per mole step, right? So overall, our delta H of the reaction is pretty decent. It's negative 23 kilocalories per mole, approximately. Only issue is we have to first do step one, which is very endothermic, followed by step two, which is very exothermic. So what does this mean for us? Well, essentially, the same delta H would be true if this went through an SN2 reaction, right? If you were to do BDEs and calculate it, it would end up being the exact same. But if we take a look at what it would be if we had in the blue line, we will call this the SN2 pathway versus in this case the red line, which is going to be the SN1 pathway. For energy, this is what we would see, right? Reactants start out up here, and products are going to end all the way down here because we know the delta H of the reaction is negative 23 kcals per mole for both SN1 and SN2. We already discussed for SN2, it's this huge peak that has a very high activation energy. But if we look at the SN1 pathway, the activation energy is actually much lower. But the thing is, it has to reach this intermediate in between before doing this, right? And then from here, it's a very low activation energy barrier to do the proton transfer, right? Or sorry, the attack on the carbocation. From here, we generate this I2, which then does the acid-base chemistry proton transfer, which is the exact same energy as the products. It just has this little activation energy step in between because it does have to go through a transition state. So essentially what we're asking ourselves is, okay, would this reaction prefer to take this path here where the activation energy is lower, or would it prefer to take the SN2 path where the activation energy is absolutely ridiculous? And of course, it's going to choose the stepwise path of going through these multiple intermediates. Because essentially what we're saying is the stepwise path is much lower activation energy and thus much faster. All right, but one thing to keep in mind is it depends on the nucleophile, right? Because your difference in energy between the reactant and I1 is always going to be the same, right? It is always going to be leaving group leaves. But your activation energy for the SN2 pathway decreases because you are increasing the reactivity of your nucleophile. All right. So this idea entirely depends on your nucleophile, right? Let's take, for example, another reaction, right? Which would be the same reaction here, but instead of using methanol, we use methoxide, right? If we're using methoxide as our nucleophile, and we're looking at the SN2 versus the SN1 pathway, SN1 still requires us to go up to that first intermediate, which is always going to be that same plus 68 kcals per mole, right? Because it's always going to be that leaving group leaving. And then from there, it's going to drop down. We're going to end up in a position where, of course, our products are the same energy as the SN2 pathway. But for methoxide, we now have a much lower activation energy for the SN2 pathway because this is already a higher energy value in general. All right. So what we're saying is weak nucleophiles prefer SN1, whereas strong nucleophiles prefer SN2. All right, that is a very important statement to keep in mind. And it all has to do with that activation energy. Okay? So, keeping this idea in mind, the question now becomes, why is it that the reaction does not stop at intermediate 2? Right? Because notice in every case, it is the exact same energy. Right? And if something is the same energy, we would expect that there would be no reason for this to go over that activation energy hump to move onto the products. But it clearly happens. The question is why? And the answer boils down to everyone's favorite Gen Chem concept, Le Chatelier's principle. Right? Essentially, what Le Chatelier's principle says is that equilibrium is shifted in a direction to offset a change, right? And this is the reason why we actually use the solvent as our nucleophile. Because if we look at this reaction from this perspective, and we look at that uh, acid base step, right? The reason that the methanol comes in here and takes this proton is not because it creates a more stable product. Right? If we were to use pKa's to justify this, right? Thinking about the acid-base chemistry lectures from a while back, the pKa of this first molecule here is about 16. The pKa of this conjugate acid is about 16. So equilibrium should theoretically be a 50-50 in either direction. However, with the methanol being our solvent, essentially what this is saying is that there are millions of the methanol compared to our acid, right? And so what that means is that we have more reactant and therefore we push equilibrium towards products. All right. So more reactant means that equilibrium is pushed towards the products, and vice versa would also be true. If you had more product, equilibrium would be shifted towards the reactants. That's just Le Chatelier's principle in general. All right, so more reactant pushes our equilibrium to products. Okay, so that's the reason that that shifts in that direction. All right. And so essentially, when we're looking at this reaction, once it starts, it's generally going to go straight towards products. All right. But the thing is, this reaction is very dependent on the substitution pattern, just like SN2, right? So our activation energy is dependent on carbon substitution. And this is why we talk so much about the carbon substitution recently, because both SN2 and SN1 are affected by it. And you can think of it like this. So in the case of the reaction that we were looking at here, right, we were saying that the first step is that our bromine leaves and we generate this carbocation with the Br minus. All right. And we've already said that the delta H of this step is about positive 68 kilocalories per mole. In terms of energy, we know that is endothermic, right? And on an energy diagram, it's going from the reactant to this intermediate one, right? And that is, of course, an uphill battle. But whenever we're thinking about activation energy, as you all know, we think about Hammond's postulate. All right. And so our transition state is closer to products, so it looks like the products, aka I1. All right. So when we're looking at this transition state for this reaction, what we would see is we're breaking that carbon bromine bond, and that's the only thing that's changing, but we're ending up with a negative charge on the bromine, a positive charge on the carbon. And since it looks like the products, and we see the products are dissociated, that means this bond right here is long. All right. And whenever we see long bonds, we think, okay, so the charges reside more on the things that the bonds are long for, right? So in this case, that's telling us that there is more of a positive charge on the carbon, which is important to know. Because now, if we think about this in terms of the carbon substitution pattern, it reveals an interesting trend, right? Think about it. If we look at a primary carbon, what we'd see in our transition state is the carbon bromine bond, of course, still being long, is going to have a partial positive on a primary carbon. Right? In a secondary, that is the transition state that we just saw, we have more of a carbocation on a secondary carbon, right? Because we have that long bond there. On a tertiary, what we would see is with that long bond, we have more of a positive charge on the tertiary carbon. So what does this all mean for us? Well, essentially, think about what we talked about a while back with radicals, right? These transition states are all comparable to essentially a molecule that just has a positive charge on whatever carbon it is we're talking about, right? And remember that these are just a way to um, accentuate what the transition state is more towards. It is not saying that this is the actual transition state, right? And we know, based on our previous talk with radicals, that tertiaries are the most stable, right? Because if we think about what this looks like, right? If a carbon has a positive charge, it has an empty p orbital. Those carbon-hydrogen bonds that are surrounding it, the more of them there are, the more can do donation. And as we know, this donation is called hyperconjugation, right? And the more CH bonds we have around means more hyperconjugation. So keeping that in mind, we know that tertiary is more stable than secondary, which is more stable than primary, right? So tertiary would be our most stable carbocation. whereas primary would be the least stable carbocation. And remember, this also follows the other rules of radicals where if you have resonance, it is even more stable. So looking at this idea in terms of our reaction diagram, practically speaking, all of these are going to have a very similar product energy, right? For now, we're going to assume they are the exact same, and they'll all have a very similar reactant energy, right? And so for this, if we're looking at primary in blue for our leaving group, secondary in red for our leaving group, I will write down and make sure that it's clear that this is for leaving groups only, and orange for our tertiary leaving group. What do we see? Well, we see that the transition state is stabilized by the more stable carbocation. So the tertiary is going to have a relatively low activation energy, right? Compared to something like the secondary, right, which is going to have a much higher activation energy because it's not as good at stabilizing the carbocation in the transition state. Keep in mind, though, that these all go through and they meet up with the same second intermediate approximately, right? It's not exact, it is approximate. Primary is an even higher activation energy before it drops down and meets up at the same intermediate too. Okay? So what this means is that practically speaking, the more stabilized carbocation gives us a more stabilized transition state and thus gives us a lower activation energy. All right? And what this actually ends up doing is, even though this isn't drawn to scale, the primary activation energy is too high for Sn1 to occur. Which brings us to a really interesting situation, right? Because in our relative rates of reaction, what we see is that tertiary is much faster than secondary, which is much, much, much faster than primary for Sn1, right? Primary will not happen. Notice that this is the exact opposite of Sn2, right? For Sn2, we were worried about tertiaries because they have so much steric bulk around the transition state. In the case for Sn1, though, sterics does not matter for us, right? Because whenever we generate that carbocation, no matter what, it is trigonal planar, it is flat. The only thing that matters for us is how stable is the carbocation. So in this case, it's the exact opposite of Sn2, where it can't do primaries, but it likes doing secondary and tertiaries. But remember, for Sn2, we couldn't do tertiaries. It was better for primaries and secondaries. All right. With that being said, we also have a rate law that we need to talk about, right? We talked about it a little bit in Sn2, but we're going to talk about it a little bit in Sn1 as well. Because essentially, when we're thinking about an Sn1 reaction, we're thinking about what is going to be the rate determining step. There are multiple now. And in all of our energy diagrams, what we have drawn so far is that from our reactants, we go up a lot and we end up with our first intermediate. And then the second step is very, very quick and easy, right? And the reason for this is because this spot here is generally low sterics and pretty much perfect electronics, right? So it has a really low activation energy. What that means for us is the first step is our rate determining step, right? And remember, our rate law is based off the rate determining step. So what happens in the first step that we've drawn many times already is just that our leaving group leaves. And as a reminder, when we're thinking about rate laws, it is always just the reactants of the rate determining step that contribute to the rate law. So in this case, the rate of an SN1, we always have K, right? Because K is the general rate constant times the concentration of the reactant. And since there is only one molecule here, that is why we call it unimolecular substitution. All right. Remember, it's not about the number of steps that we see, it is about the number of molecules in the rate law. Okay. So that's great. We've talked a lot about how SN1 actually works, right? It's always just leaving group's going to leave, next thing's going to come in, add in, then you get that proton transfer. But the thing is, we haven't talked about one last piece, and that is stereochemistry. Right? When we're thinking about stereochemistry in SN1, it can also form things that are chiral, right? Think about if we had this bromide here. And you know what? We'll even give it stereochemistry to show that it is chiral. If we were to take this and mix it with ethanol as a solvent, what we would see is that we would end up with this guy on a dash, right? Which we would expect from something like SN2. But we also end up with the same thing on the wedge. And as a matter of fact, it is a 50-50 mixture, right? Which tells us that it is a racemic mix. The question is why? Well, if we take a look at our mechanism, we can suss out why this is the case. Taking a look at our starting material, right, with the bromide, it starts out and it is, of course, chiral, right? It has four different things attached to that carbon. Currently, it is sitting as, what would this be? It would be R, right? A nice chiral center that is R. But upon the first step occurring, which is the leaving group leaving on its own, right? It takes those electrons and it pops off of there. You end up with a carbocation. This carbocation we've already described is stabilized by hyperconjugation. And the reason why is it is sp2, it's trigonal planar. As a reminder, whenever we're looking at things that are planar and things that are sp2, we always say that they are achiral, right? It loses all chirality when the first step happens. But then the second step happens, right? This ethanol comes in and it adds. Upon doing so, we have created a new chiral center, right? Because now this is back to being sp3. It has four things attached. This is now chiral. So how do we get to the 50% wedge and dash? It's actually the same argument that we used for our radicals in terms of radical halogenation, right? Whenever we're looking at the carbon in the carbocation, it's an empty p orbital. It's got three things attached to it. It is planar. So upon having our ethanol or whatever nucleophile it is come in, it can either go into the top part of the p orbital or it can go into the bottom part. And the thing is, it's statistically equal the same way, right? It 50% of the time will go up top, 50% of the time it'll go to the bottom. It's like a coin flip, which one it does. And so what this ends up doing is this 50-50 is what ends up creating our racemic mixture, right? And it's the exact same argument as the radical of you can attack above or below, and whichever side you attack on ends up giving you the appropriate wedged or dashed product. All right. So in terms of stereochemistry, unlike SN2, this one does not care about stereochemistry. It clears it and it just gives you the racemic 50-50 mix of products. All right. Now then, one other thing that's important for SN1 is solvent dependence. So one other reason that the solvent is the nucleophile is not only because of that second step that we talked about, but it's because polar protic is important for us here, right? So the solvent is always polar protic and the weak nucleophile. So if we think of the first reaction that we drew today, we were saying the alkyl bromide there with methanol ends up doing stuff. It ends up making that product. Well, the reason for this is the solvent actually also stabilizes the intermediate. And how it does this is when the bromine leaves, right, we end up generating the carbocation and Br minus. But thinking of bromine with a negative charge, we already actually looked at bromine with a negative charge, sort of. We looked at iodide beforehand and the way it interacts with water. And the way it interacts with methanol is very similar to the way that iodide reacts with water, where all of these methanols have that partially positive hydrogen that can be donated through hydrogen bonding. And so essentially what this is doing is the H bonds are stabilizing the negative charge. And what that's doing is essentially, if you're thinking about this in terms of energy, if you could run an Sn1 reaction in a polar aprotic, right, we will list that in blue, right, if it was aprotic, versus in red in this case, if it is protic, what we would see is, all right, starting from the reactants to the products, the reactants will all be the same energy, but the second we go to an aprotic solvent, we get this huge increase in what I1 ends up looking like versus in a protic solvent where I1 is very stabilized. All right, so essentially, the solvent being the nucleophile is important because it can get rid of its proton because after it attacks, keep in mind, it still has that, in this case, OH that it needs to get rid of. So that's telling us that this is necessary, but it's also telling us that it's necessary for the stabilization of whatever leaving group it is that left. Okay? So, overall, what do we know so far? We're going to give a quick overview, comparing the two reactions that we've talked about thus far. So first, we talked about Sn2, where Sn2 needed strong nucleophiles. It said that primary was better than secondary for our leaving group, and we said no tertiaries. We learned that polar aprotic is better for our solvents, and we learned that it inverts stereochemistry. All right. Versus Sn1, what have we learned so far? Well, we've learned that it likes weak nucleophiles. Tertiary leaving groups are better than secondary. No primaries allowed. We learned that polar protic solvent is better. And we learned it forms racemic mixture. All right. So far, these are practically the exact opposite of one another. All right. Sn2 is the antithesis of Sn1. Now, that being said, that's the end of this lecture. In the next lecture, we're going to talk about something called E1, or unimolecular elimination. And what we're going to find is that essentially it's going to be the third piece that coincides very well with Sn1. All right, so until next time, we'll see you then to talk about E1.